It's already like. Let me turn off my video.
Good. Is that fine?
Now you're unmuted.
Okay. Thank you.
So check the.
Anyway, so what we will see is that once you generalize the classical limit, you can find new topological solitons, generalizations of the notion of skyrmions. You can find skyrmions in quantum paramagnets, so on and so forth. Once you basically generalize or you develop these large N approaches beyond, actually we will see that it is strictly necessary to go beyond the mean field level, beyond the saddle point level if you want to describe ordered magnets, for instance. Systems that may motivate you are triangular lattice antiferromagnets, for instance, where as a function of the ratio between the second neighbor and the first neighbor antiferromagnetic interaction, you can have a continuous phase transition from an antiferromagnetically ordered state, 120-degree order, into a quantum spin. And the question is, how do we describe the dynamics near one of these critical points? And we'll see that generically near non-trivial quantum critical points like this one, or more trivial quantum critical points that separate magnetic ordering from a paramagnet, it's actually better to use a large approach. So let's start, with the generalization of the classical limit. Mathematically speaking, we'll see that what that generalization entails is going from SU2 to SUN, and actually generalizing basically this idea of considering a sequence of irreducible representations and going to some infinite limit, when we send, we identify a parameter that labels the representations and we send that parameter. So that is the way we are going to generalize the classical limit. Now, let's start by reviewing the usual classical limit, right? How do we take the classical limit of a spin system? Normally, we send S to infinity. Why is that? Well, spin operators, we know that obey SU2 commutation relations. This Levi-Chivita symbol is the so-called structure constant of SU2. And the simple observation is that if we allow the spins to take different values, right? So we move across different irreducible representations of the group SU2, then we immediately notice that what's on the left of these commutation relations is quadratic in S, while what is on the right is linear in S. Meaning that to leading order in S, I can neglect what appears on the right-hand side. My operators commute, and then I can treat them as numbers, right? And the states, the basically manifold of possible, classical states becomes a manifold of states that maximize the eigenvalue of these spin operators, which are the so-called coherent states of SU2. We can build them by simply considering the highest way state, the state that has SZ equals to S, right? We are considering that state as a reference state, and then applying SU2 rotations to that reference state, right? So in that way, we will get all the possible coherent states of SU2, right? And actually, there is a one-to-one correspondence between these coherent states, omega j, and the expectation value of the three spin components, right? The observables, correct? So we can either represent the state in this way, this coherent state, or through the expectation value of the three spin operators that produces a vector of fixed magnitude. Okay? Magnitude is fixed because of the quadratic classification of the spin. So I can either represent, I can represent these states as points on the sphere, right? Given that these observables give me a normalized vector. So there is a one-to-one correspondence between points on the sphere and each of these coherent states, right? So we say that the phase space of our classical problem is the sphere, right, which is isomorphic to CP1. CP1 is basically the manifold of one-dimensional subspaces in a two-level set, right? In C2, in the two-dimensional vector space. Good. So once we have done that, we can extend the problem to the lattice, right? So the algebra of n spins is basically a direct sum of the individual algebras, and then construct coherent states, right, of these, which are simply the direct product And now if we want to write or derive the classical equations of motion, all we need to do is take the expectation value of Heisenberg's equation of motion on both sides, solve this commutator, replace, so, use the factorization rule. So the expectation value of a product of spin operators becomes the product of the expectation values in the largest limit when s goes to infinity because operators commute. And finally, we arrive to this very well-known equation that is that the derivative of this classical vector, our classical spin, is simply the cross product of the classical spin times this effective field that is simply minus the gradient of the function. Right? So this is the very well-known Lambda-Lipschitz equation that has multiple applications and interesting nonlinear physics. Of course, what one can do then, if you linearize this equation, so meaning if you find the ground state of this classical Hamiltonian, and now you do small oscillations, right? So now you replace the sphere by the tangent plane, right? To linearize the equations, you have to remember that this is the phase space. The sphere is a two-dimensional phase space, meaning that these small oscillations are coordinate and momenta. So we have one pair of coordinates and momenta per spin, meaning that we have one degree of freedom per spin. So it means that the number of normal modes that we would obtain if we do small oscillations is equal to the number of spins. And if the system is translationally invariant, the normal modes will be spin waves. We know this very well. And actually, you can get these spin waves either by requantizing the harmonic oscillators of these normal modes, or by simply representing your spin, using the more traditional way of deriving spin wave theory, which is by representing the spins as bilinears in Schwinger bosons in two flavors, obey this constraint. This constraint basically defines, fixes the irreducible representation. And then using a Holstein-Primakov transformation, basically eliminate, one of the bosons, the boson that creates this classical crowd state, right? And expanding the Hamiltonian up to quadratic, right? That is another way of deriving exactly the same Hamiltonian, the same spin wave theory. So, so basically, you have two ways, but the difference is that when you use this approach, right, you are actually working with operators. You are working with a fixed irreducible representation and actually expanding in the inverse of this parameter, right? So that expansion becomes actually a loop expansion. The 1/s expansion is simply a loop expansion. Anyway, so that is a standard approach, correct? So we all know very well from the textbooks, and it's very general and very applicable because there are many materials that behave semi-classically. Now the issue is that you can find also many examples of materials that behave semi-classically, but you cannot use this classical limit that just described. And to consider a very simple case, let's or illustrate it with a simple example. Let's consider a single ion isotropy of this kind. Let's say we have a spin 1 system. And now the ground state, because this is positive, is the Z equals 0 state. The two excited states are plus and minus. Clearly, if we compute the expectation value in this state is equals to 0 of the three spin operators, we are going to get 0, meaning that this state is obviously not a coherent state of SU2, right? We don't have a dipole moment in the ground state, so we don't know how to do small oscillations because there is no dipole to oscillate. So what do we do in a case like this one where, clearly we don't have a classical counterpart in terms of coherent states of SU2? Well, what we have to do is recognize that, if we have a spin 1 system, the most general state is an arbitrary linear combination of 1, minus 1, and 0. That arbitrary linear combination is parameterized by 4 real parameters because we generally it will be 3 complex numbers, but we can eliminate 1 through normalization and phase. And basically this set of states, right, is spanned not by coherent states of SU2, but by coherent states of SU3. Right? So we have, if we want to build, an arbitrary state like this one, we have to apply unitary transformations acting in this 3-dimensional space, the most general one will be SU3 transformations if we additionally ask that the determinant has to be equal to 1. And now, right, the manifold of coherent states, right, something that I didn't explain before, but let me explain it now. There is a subgroup of transformations that will leave this state invariant up to a phase, right? In the case of SU3, that subgroup is U2. So there is a subgroup U2, right? That transformations that will leave this state invariant. So actually, the manifold of possible states is not basically the manifold of elements in SU3, but actually it's SU3 divided by the so-called isotropic subgroup that leaves the state invariant up to a phase. So in this case, it's SU3 divided by 2. That gives you CP2, which is again the space of the manifold of one-dimensional subspaces in a three-dimensional vector space. In other words, the manifold of possible quantum mechanical states of a three-level. Quantum mechanical states are not points in a vector space, are actually rays in a vector space, right? So that's the reason why we talk about CP2 instead of C3. Good. So we can expand this to the lattice. Again, an arbitrary coherent states on the lattice will be the direct product of states. And now the difference is if I want to keep, my one-to-one correspondence between kets and observables, I need to introduce 8 observables, the 8 generators of SU3. In the case of a spin 1, I can build one physical observables. I can, you choose the 3 dipole components, the X, Y, and Z, and then the 5 bilinears corresponding to a traceless symmetric tensor. That's the quadrupole moment. So with the quadrupole and the dipole, we have a complete characterization of the ket, in the sense that if I give you the expectation value of these 8 observables, you can tell me what is the ket. It's a one-to-one correspondence between observables and kets. All right. In particular, for the state that I was considering before, that state has 0 dipole moment, but has a net repellent moment. So that is the reason why you cannot describe it, in terms of the standard SU2 classical theory, but you can. I mean, this is a classical example of a state that has an equipolar moment. Zero. Good. So now we need to introduce a classical limit. And again, the trick is always the same. The difference now is that the irreducible representations of SU3 are labeled by 2 parameters, not by 1, as in the case of SU2. And these 2 parameters are lambda 1 and lambda 2. Lambda 1 and lambda 2 are actually eigenvalues for the Cartan Saval-Shura. Right, the Saval-Shura operators that commute with each other, and actually, what you can verify in this case is that if you put lambda 1 equals to m and lambda 2 equals to 0, you get basically a sequence of irreducible. Yes.
Sorry, you said there's a one-to-one correspondence between ket vectors and observables.
Yes.
And that's so that observables correspond to Bayesian operators. So what's the
Yeah. So these are 8 Hermitian operators.
The ket vectors are the states.
Sorry.
Sorry. Yeah. So,
Yeah. So these are 8 Hermitian operators. What I'm claiming is that if you give me the expectation value of these 8 Hermitian operators, I can tell you what is the ket, what is the coherent state. So there is a one-to-one correspondence between the 2 things. It's like Heisenberg picture versus Schrödinger picture in the classical. Good. So now we can consider this sequence of irreducible representations. If you want to see them in terms of Young tableaus, this particular sequence. Actually, what is important about this sequence of representations is, first of all, m equal 1 corresponds to the 3-dimensional fundamental representation of SU3, the one of interest if you want to describe a 3-level system. And then these other values of m correspond to completely symmetric irreducible representations that actually have the same set of coherent states, right? Actually, the manifold of coherent states of a Lie group depends on the irreducible representation. So this is the sequence of irreps that all have CP2 as the manifold of coherent states. And now the argument is the same as before. What I have on the left-hand side of the commutation relations of SU3 is quadratic in M, but I have on the right-hand side is linear. So in the large M limit, I can neglect this in comparison to these operators commute, and I can replace them with excitation. Good. So now, yes.
In one of your first slides, you had the picture of something topological. And experiment.
Yeah.
So now you've already changed your manifold.
Yes.
I guess the topology has also changed.
The homotopy group.
Yeah, exactly.
Yeah.
This is going to be, are you going to restore the same topology as for S2, or are we going to forget about?
We will see. We'll
Okay.
see. Yeah, just
Okay.
bear with me for a moment. Yeah, that's an excellent question. Yeah. Actually, yeah, the homotopy groups will depend on the manifold, right? So for each classical limit, it will be a different homotopy group. And yeah, so you can get different topological limits. So anyway, so now the important thing is now my generalization of the classical moment is actually this so-called color field. That's the name they use in high energy, which is the expectation value of the 8 components, right? The 8 generators. 3 of them are dipole moment, the other 5 are quadrupolar. And now I can do the same that I did before, take the expectation value of the Heisenberg equation of motion and derive this generalization of the Landau-Lifshitz equation. Well, as you can see, it is a generalization in the following sense. My now classical variable has 8 components, and my cross product has been generalized because instead of being the contraction, right, with heavy Civita, that is the structure constant, which are the structure constants of SU2, now I have the structure constants of SU2. Yeah.
So here your strategy is to take higher symmetric representations of SUN. Is that the strategy?
The strategy in this particular case is to take the completely symmetric irreducible
There are
representation.
many other ways you could do this.
But then there are many other ways. You're absolutely right, and we can discuss it in the discussion. The manifold of coherent states will change.
Yeah.
So for instance, if we take that joint representation, it will be a flat manifold.
Right.
Right, and you may have reasons to use that classical limit. Right. We can discuss it later. You will get other topological defects.
For example, you've gone to 3, but once you go to SUN, you could take block representations, you could take totally anti-symmetric
Absolutely,
representations.
absolutely. But again, we have to keep in mind that we want to preserve the manifold of coherent states. So for instance, all of these reps have the same manifold of coherent states that is CP. If you want to take the classical limit, you send them to infinity, preserving the manifold of coherent states. You could choose those in which both lambdas are finite, right? Then the manifold will be a flat manifold. The isotropic group is U1 cross U1. SU2 divided by U1 plus U1 will give you a flat manifold. So then you will be dealing with nonlinear sigma models on flat.
But if we start from the elementary representation,
The fundamental is M equal 1.
box, right?
Yeah.
We don't really know what direction we should extend the
We do.
expansion.
I will argue that we do, because for M equal 1, the coherent states.
To give you an illustration, you can look at magnetism by taking symmetric representation, which is the direction you're going. But you can also take anti-symmetric representation, which is the natural way to go for say, the Kondo fault.
I agree here, but what I'm saying is,
There's a physics motivation coming in here, and I guess that physics motivation is to be close to magnetism.
yes, but all I'm saying is, I fully agree with what you're saying. I'm just saying, to take the classical limit, you want to preserve the phase space, the structure of the phase space when you send that goes in to infinity.
And what I'm saying is there are many, many different classical limits.
Absolutely, I'm saying the
a
same
very
thing.
particular one.
I'm saying exactly the same thing that they are saying. Exactly. So there are many classical limits. This is a particular one, right? And for each classical limit, we'll find different topological effects and a different equation of motion. Good. So anyway, so let's continue. So anyway, so in the same way we can generalize the Landau-Lifshitz equation of motion. You can add noise and dissipation, again, through the same generalization of the cross product and generalize the Langevin equation, right? So you can define a Langevin equation. And actually, I told you that there is a one-to-one correspondence between gets and observables. So you can write this equation in Schrödinger's picture, basically as a Schrödinger equation for the evolution of the ket, of the coherent state. And basically, you know, the Langevin equation will be simply a stochastic Schrödinger equation where you have noise and dissipation through this procedure. And actually, Schrödinger's picture is better if you want to implement this numerically. So it's more efficient to work in Schrödinger's picture than in you know, Heisenberg's picture. Now, I mean, you can do the same thing that we did before. You can take the classical, I mean, after taking the classical limit, you can minimize the energy, right? You can minimize the classical Hamiltonian and then do small oscillations. But now, because our phase space is four-dimensional, the tangent space is also four-dimensional, and we have one pair of coordinates and momenta, conjugate coordinates and momenta, right? You know, per spin, meaning that now we have two collecting modes for spin. One corresponds if you want to oscillations of the dipole moment, the other one to oscillations of the quadrupolar moment. Right, so the number of collecting modes is different now because you know we have a larger arrangements. And again, we can introduce three flavors of Schwinger bosons for SC3, represent all the generators as bilinears in these bosons, write down a Holstein-Bimmelkopf transformation where this parameter m now appears here because you know the number of bosons tells us you know, what is the irreducible representation. These are precisely all the completely symmetric irreducible representations of SU3, and then expand in 1 over m, which is simply, once again, a loop expansion. Right? So you can add quantum corrections by expanding. But you know, one important thing to notice is that there are two different approaches here. One is to take a classical limit and m to infinity, right, and derive a classical theory. Another one is to fix m and expand, you know, 1 over m, where basically you are still using operators, right? You're not taking a classical limit when you do this. This problem still has combinatorial complexity. The advantage of the classical limit is that, you know, the cost of solving the dynamics, of solving the equations of motion, scales linearly in the number of spins. And that's what makes classical approximations very powerful, right? You replace the exponential complexity of a quantum mechanical problem, you know, with linear complexity in the number of spins. Good. Examples, you know, why this is useful. Let me consider a very simple system, you know, an Ising-like magnet. I'm not going to, you know, give many details, but, you know, it's a triangular layer system with multiple competing exchange interactions. The system has a strong single ion EC axis anisotropy, and the magnetic ordering is this kind of stripe ordering where you have ferromagnetic chains, antiferromagnetic chains. Turns out that, you know, because this anisotropy is rather large, when you do a neutron scattering experiment, what you find is two modes instead of one. Remember, for SU2, you expect two modes instead of one collective mode. But if you do the linear spin wave theory, you will say, well, it's an Ising magnet, you know, more classical than that you cannot find, right? But actually what you get, of course, if you do linear spin wave theory, is only one collective mode, you know, spin waves, which clearly contradicts this observing effect. And the answer is that, you know, actually, if you go to SU3, you find an excellent agreement, because what is going on in the system is that besides the dispersive spin wave mode, the fluctuations of the dipole moments, you have a quasi-flat quadrupolar mode that is crossing, right, you know, this band, right? There is a finite hybridization because the Hamiltonian does not conserve the total magnetization along the z-axis, and that hybridization opens a gap, pretty much like in the Higgs-Fermion problem. And now what you have is a hybrid mode, which has, you know, strong quadrupolar character in the regions where it is flat, quasi-flat, and strong dipolar character in the regions where this is going. And that is precisely the reason why you can observe it with neutron scattering. With neutron scattering, you can only see dipolar fluctuations, but because of the hybridization, this dark or the polar mode becomes visible, right? And you can see that, okay, so if you use this SU3 dynamics, you are going to capture the whole. Of course, you may say, well, this is just a generalized linear spin wave theory that goes under the name of multi-flavor spin wave theory in the literature and has been known since the 60s, right? But the difference is that, oh, yes.
But, Cristian, I just had a question. In principle, when regular spin wave theory, don't you get this when you have to do a very high order?
That's an excellent question, Premi. Yes, you need to go to infinite,
That's what I mean.
right? Because you need to sum the full ladder diagram, meaning that in this loop expansion, you need to sum diagrams that go to infinite order in the number.
So you could get this, but it would be a lot
It will be a lot of work.
work, right? So your
So
point is that.
this you get it
But
the
in
linear level.
principle, it is there in regular spin wave
Absolutely.
theory, but you have to dig it out.
Absolutely.
Okay, thank you. I just wanted to.
You
Also,
also
no
have
natural small parameter in regular spin wave.
Yes.
yeah, that's an excellent.
So
So
can I ask a question about
yeah.
iron? The iron is a quartet.
the ion is spin one. This is
Sure.
anyway, what I mean, and again, this is so this is just linearized dynamics. This goes in the literature, and the multi-flavor spin wave is just a generalization. Multi-flavor spin waves is the generalization of spin waves from SU2 to SU. The interesting thing is that if you, let's say now increase the temperature and go into the nonlinear regime, when the fluctuations are not Gaussian anymore, right? So spins are fluctuating widely, then you cannot linearize the equations of motion. But, since you have the classical equations, you can access the nonlinear regime, you can try and see if your classical equation, your classical visualization of the classical equation of motion, of the Landau-Lewis equation of motion, can account, right, for the dynamics over the full temperature in the region where the nonlinear effects become equal. And actually it can, right? So this is the experimental data for different temperatures, and this is what you get with this SU3 generalization of the Landau-Lewis equation of motion. This, for your reference, is what you will get if you use the standard Landau-Lewis equation of motion in terms of dipoles, right? You miss basically this finite frequency region, right? And you get a peak actually centered around zero. It's not only you get the wrong behavior or quantitative behavior at low temperatures, you cannot reproduce the high temperature dynamics, and you can, right? With this generalization of the Landau-Lewis dynamics. But perhaps, what is more important.
How does the physics know whether it's in a symmetric representation of SU2 or a fundamental representation of SU3, which is what we were really treating it as?
Yeah,
How
so,
does it know?
well, these are, like you said, two different classical limits. They have different numbers of modes.
Right, so why is it, I guess I'm asking, why should we expect it to be closer
Ah,
for the SU3 than the SU2? in terms of-
well, because, for instance, in the single ion physics, even in the high temperature limit, you have this splitting. Let's say the high temperature limit is single ion physics, you will still see this mode, right? The transitions between the doublet and the singlet is something that you will not capture in SU2. In SU2, you will get a diffusive mode centered around zero frequency, but in SU3, you will get this frequency.
And how big is that splitting?
It's V, right? So
No.
in the problem is basically this energy scale is basically of the order of 5 millivolts. Right? So
Okay, so that's the answer to my
That's
question.
the answer.
It's essentially a triplet ground state with a small splitting.
right, so it's a simple example to see why you may want to use this classical period.
But it's still a little bit mysterious that it's different. That it's closer to SU3 than it is closer to SU2.
Well, with SU2, you will never capture this. With SU2, you will get a completely diffusive behavior at different temperature for the dipole.
Oh, but SU2 still has a triplet present at spinning as well, right?
It does, but classically what you will get is a dipole fluctuating in a completely random field.
Sure.
You will get a diffusive peak center around zero. There's no way you will get a characteristic frequency.
So you're saying that the synthetic classical limit of SU3 is closer to the physics of the SU2 system, and it's remarkably in its symmetric representation.
Tangential, but if the excited states were adapted, you would in principle go to SU4, but then actually SU2 would be the better representation. It would be again this representation. So if the excited state were adapted, okay, so would you well, naively now you would probably think of some SU4 physics, but the SU2 probably would be a close enough. No, because again, the SU2 will give you a diffusive peak center around 0 point. So if you saw we again center around 0, if that's center around 0, yeah, even if you have a direct here. Right, so you would have the physics of a dipole fluctuating, I mean, precessing in a completely random field that will give you a diffusive peak at 0. So, I mean, we can discuss it later. That's a good question. Good. Anyway, so now why do I care about nonlinear effects? Well, you know, some of the physics that, you know, nonlinear physics or physics of these systems is topological solidons. We know, you know, since 2008 that skyrmions, magnetic skyrmions can appear in condensed matter physics. And actually, the way we think of them is, you know, think that you have a film to the system, you can map, you know, to use a stereographic projection to map the plane into a sphere, assuming that we are going to consider solutions that are constant at infinity. And now, because we have one spin on every point on the plane, we have a mapping of the sphere into the spin. To each point of the sphere, we assign a classical moment that is a vector with a fixed magnitude. And now what we can do is we can count how many times this mapping of the spin into the sphere is wrapping the sphere. And that is simply the integral of the density of solid angle, right? Which is precisely this quantity. This is the density of solid angle. I integrate over the full plane. I get the number of times, you know, if I divide by 4π, the number of times that this mapping is wrapped in the sphere. We call that skyrmion number. And actually, the homotopy group associated with these mappings is the integers, right? So we call it second homotopy group by 2 of its 2 is 8. Now it turns out that, you know, the second homotopy group of CP2 or CPN minus 1 in general is still the integer, right? So if you go and check, right, if you classify the mappings now from the sphere that represents my compact amplifier to the system into CPN minus 1, that is my phase space of these classical theories, that is still the integers. So we can generalize the notion of skyrmions. And now you can see the way we generalize the skyrmion number is once again replacing the Levi-Civita that was implicit in this contraction with the structure constants of SU. Correct? So this integral is quantized, and now you can have objects that are purely dipolar in the North Pole, right? And purely quadrupolar in the South Pole. Right? So you can get
8π or 1 of them.
This,
Just by analogy.
yeah, no, well, this is because I'm using a different normalization of these fields. But it depends on how do you normalize these fields.
So you're not using a unit normalization.
No. So it depends on the. But yeah, that's a good observation. Anyway, the interesting thing is that, you know, this you will say, well, it's a mathematical observation, but actually you can take a very simple speed-1 model where you have competing ferromagnetic and antiferromagnetic interactions in a triangular lattice, and also competing anisotropies, single ion and exchange anisotropy. And with this simple Hamiltonian, you can get the skyrmions both as metastable states of a quantum paramagnet, and also you can get a skyrmion crystal as the ground state. Right, and I will not describe all the details, you know, for those who like take continuum limits. When you take a continuum limit using this classical limit based on CP coherent states, what you get is a nonlinear sigma model in CP2 in this case. These nonlinear sigma models are studied actually in high energy in the context of topological solidons. And actually, when you know, as I said, there is a regime of this Hamiltonian where you get skyrmion crystals that, as I said, near the core, for instance, are magnetic, and in the periphery, they are purely quadrupolar, or the opposite, In the core, they are purely quadrupolar, and in the periphery, they are magnetic.
What sets the lattice spacing in your swimming crystal?
The ratio between J2 and J1. So I told you that you have two competing interactions, and that sets the lattice spacing. Thank you. Okay, and moreover, this Hamiltonian in the large, the limit D is easy plane, and isotropy will favor this SZ equals 0 state everywhere, a quantum paramagnet. And you can demonstrate that, this kind of skyrmion, right, that is now a metastable state, right, is metastable actually. So, for a quantum paramagnet, a vegetable where you have SZ equals 0 everywhere, you can get a metastable skyrmion state, which near the core is magnetic and far away is still quadrupolar. Moreover, I told you that you can get crystals because you can solve the classical equations of motion. You implement this Lange-Johann dynamics. You can study how these crystals evaporate, right? And at high temperatures, you still have skyrmions creating an annihilation, right? So that's one of the nice aspects of generalizing these classical equations of motion.
Sorry. Yeah. So for the CP1 case, you get these like hot, like three-dimensional defects as well. Am I right thinking there's no analog for CP2?
Yeah, absolutely right. Yeah, for that there is no answer. Excellent. So, yeah, we can discuss it. Anyway, so if you ask now, how many real materials, will require, this generalization of the classical limit, you will find many. Actually, you can think of systems like this one, just a simple ladder with timers. The natural thing here is if the ladder is a one, for instance, we know that when the coupling along the ranks is dominant, you have again a quantum paramagnet that is roughly a product of singlet states. And the right thing to do there is to treat each timer as a 4-level system. You use SU4, right? The Landau-Lucius equations, and actually you can demonstrate that that works very well at low temperatures if the inter-dimer coupling is weak compared to the intra-dimer, but at high temperatures in any situation, right? So there is a quantum, although the ladder, we know that the entanglement grows as we increase the coupling between the dimers. As we increase the temperature, there is a quantum to classical crossover, and the classical, approach works very well above a certain crossover.
Can I just ask a question on the skyrmion crystal? So you need to apply a field, right, to get the skyrmion
Absolutely.
crystal. And then within the skyrmion crystal, as a function of field, you change the size of the dipolar core compared to the quadrupolar shell, or
No, the size of the dipolar core does not change. The field changes, gives you, actually by changing the field is that you can go from this skyrmion crystal to this skyrmion crystal, but the size doesn't change. The skyrmions, normally in these ways of getting skyrmions, the skyrmion size does not depend on the magnetic field.
No, but within the skyrmion, you said you have the dipolar core, and then
Yeah, sorry, yeah, the dipolar core, and then, far away in the periphery, you have a quadrupolar region, right? So this region here is purely quadrupolar. Good. Okay, so I told you about, how to generalize the classical limit. Okay, as you can suspect by now, in the same way you can generalize the classical limit, you can generalize the largest n limit. As you saw, the way you generalize the classical limit is you consider, different Lie algebras, SUM instead of SU2, and then you always send the reducible representations to infinity. Now, what you can do in a large n approach, what you will do essentially is send n to infinity. Your control parameter will be dictated by the group and not by the representation. Okay, and the reason why you may want to do that is because sometimes you have systems in close proximity, for instance, to a quantum spin liquid. This is Heisenberg antiferromagnet. It's a phase ion of Heisenberg antiferromagnet with nearest and second nearest antiferromagnetic interactions. And the MRC tells us that there is a quantum critical point, so a continuous transition into a quantum spin liquid. As you can imagine, the dynamics of this ordered magnet near this point cannot be described semi-classically, because magnons are continuously getting deconfined into spinons, which are the true collective of elementary excitations of this quantum spinning set. So what do you do in that case? The classical approach fails. And the approach that we have been following for a few years is the idea of starting from a theory of non-interacting spinons. So you start, let's say, from something that will work really nicely in the spin liquid phase and recover the magnons as two spin-on bound states. But of course, if you are going to follow that approach, you need to go beyond mean field, because at the mean field level, these theories will give you free spin-ons. So the only way you can recover the magnons is by considering the interactions. And that you can implement using the so-called Schwinger boson approximation, right, which is a Laplacian approach, where you still represent the spins as bilinears in Schwinger bosons. But the difference now is that instead of condensing individual bosons in particular sites, we are going to consider bond operators, fields defined on bonds, and treat those basically as numbers, and then fluctuations of those numbers. So in other words, we are going to write the Heisenberg Hamiltonian as a bilinear in bond operators. In particular, for this AC2 case, you have these two bond operators, which are singlets under the symmetry group, which is AC2 of this Hamiltonian. So we represent this in this way, and the strategy is, again, to introduce some Haber-Statorowicz transformation to basically make this Hamiltonian quadratic at the mean field level, right? And then, expand by, introduce fluctuations of these, bond operators for Haber-Statorowicz. And to implement that, you need to go to a path integral formulation, where you use coherent states of AC2 again to write this path integral, and you need to introduce sources and then a symmetry breaking field, because in this approach, the way you get the magnetic ordering is through spontaneous condensation of your bosons. The same way an ideal Bose gas, will condense at a finite temperature in 3D, of course, at 0 temperature in 2D. Here we'll get the magnetic ordering via condensation of these Schwinger bosons that will be the spin-ons of our field. So the procedure is the standard one, right? You write the path integral formulation. You apply a Haber-Statorowicz transformation. You introduce these W fields that are the bond operators, and these B fields still contain the Schwinger bosons. And basically, you write, the partition function. After integrating out the bosons, you can write the partition function as this determinant, this complicated determinant in terms of these Haber-Statorowicz fields, and then expand this, around the saddle point, right? And basically, what you recognize is that because you are describing the spins as bilinears in bosons, there is an emerging gauge symmetry. So you can multiply each boson by a phase, and that will not change the spins. And of course, because these Haber-Statorowicz fields are bilinears in the bosons, they are also transformed. They have the gauge transformation, they transform in this way. And you can see that the gauge fields are basically the phases of these W fields, and also the Lagrange multiplier we need to introduce in order to enforce the constraint. Remember, the Schwinger bosons obey a constraint that is, of course, the Lagrange multiplier. So this is a bit technical. Normally, you expand the action, up to quadratic order and beyond, right? So this is the Gaussian part of the action, and basically at the saddle point level, if you only keep the action at the saddle point level, then you get a free boson theory with a propagator, right, for the Schwinger bosons that contains a non-condensed part and a condensed part. And that is very important. If there is magnetic ordering, there is a condensation, so there is the Gliese function of your bosons as a condensed part. And that is important to keep in mind because, it brings some important it has some important technical consequences to understand the dynamics of the ordered state. So this is the basically the dispersion relation of the single spinels that you get at the quadratic level. And if you want to go beyond the saddle point, you need to construct, your diagrammatic technique for which, you have two types of propagators, the single boson propagators and spinel propagators, and also the propagators of the Howard-Fulton-Edge fields, which is basically the inverse of the fluctuation matrix associated with this action that, I was describing before. And then you have external and internal vortices, the external ones associated with the external sources, and the internal ones that, basically account for the effective interaction between and the fluctuations of this Howard-Fulton-Edge field. So anyway, at the saddle point level, right, what you get is what I was anticipating. If you excite the spin decays into two spinels, the spinels recombine and come out. And because there is a condensate, you can represent one of these lines with a condensate. And then if you are computing the magnetic susceptibility, the dynamical susceptibility, which is what you measure with the electric neutron scattering, you will see poles, but those poles are not magnum poles, are single spinel poles. And this is something that was missed for a long time. If you are working at the saddle point level, there is no way you will get poles associated with the true collective modes of an ordered magnet, which are magnets, not spinels. So in order to recover the true magnets, actually you need to go beyond the saddle point level. Add these 1/n corrections. These will be the diagrams that are 1/n corrections to this diagram. But here what is important, because you may say, well, how a 1/n correction will fix a problem that appears at order 1/n to the 0. But it turns out that in the presence of a condensate, these 1/n diagrams, this one in particular, contains a singular contribution that is of order 1. Right? That is a crucial observation. And it is such that it will exactly cancel the residues of the single spinel poles of this diagram and will leave you only with poles coming from the RPA propagator, from this wave, which are the true collective modes. Those poles are the magnum. So the magnum poles are inside this propagator, and the single spinel poles that are contained in this diagram are exactly cancelled by this part. So what happens in these theories is that for each diagram, there is a counter diagram. You need to add this kind of spade, right, to cancel the single spinel poles and get the true collective modes of the field. This is an example of how that happens. Saddle point level basically is the dashed line. When you add this counter diagram, you get an exact cancellation of the poles. Now you get true and a new pole associated with the wave. And for you to see how it works, if you have an actual experiment, this is experimental data in an antiferromagnet, in a triangular lattice antiferromagnet, particularly this material. You can see that, this is the magnum dispersion, this is the continuum. I mean, one important thing is that there is a very high intensity in the continuum is actually significantly higher than the intensity under magnum peaks. That's the indication that the system is close to one of its quantum critical points. And actually, if you do only saddle point, you get this mess. You get this, spurious modes. But once you add the counter diagram, you get something that looks very similar to this.
This is three-dimensional?
This is two-dimensional. Actually, you're right. I mean, so there is some small coupling between layers, and it is included. Yeah, this is two-dimensional, but the interlayer coupling, I think, is 3% of the instrument.
So how can you distinguish the continua? How can you distinguish that these are continua from two magnum continuum?
I mean, that's a very good question. So first of all, the continuum extends way more than twice the single magnum bandwidth. That's an indicator that probably it's not.
But in principle, you can have both, right? And you need to disentangle some.
Yes, in this theories, okay. So I mean, that is true. You can have both, and actually, in a theory like this one, you will have two magnum continuum. But the question is, how much intensity comes from the two magnum continuum versus the intensity that comes, from the multi-spinel continuum. Mm-hmm. And maybe, okay, so let me go to that point, in a moment. I mean, this is the comparison directly. If you extract the magnum dispersion from the experiment that was basically done by Gadufol through a phenomenological fit, these are the circles, and what the full line corresponds to the Schwinger boson dispersion. And this is actually an example where if you do nonlinear spin wave theory, you cannot reproduce the Magnum dispersion, and moreover, you cannot reproduce the relative magnitude of the continuum. What you get in nonlinear spin wave theory is that the intensity in the continuum relative to the intensity under the Magnum peaks is 2/3, while in the experiment is actually 2.8. And in the Schwinger boson approach, you get very close. The problem is in the Schwinger boson approach, you get this first peak, right? That appears as basically the two spin continuum, but you don't get this other peak, which is great, that has to do with higher four spin continuum. Basically processes that will require to add more diagonals. But what the reality is that this is the first case that I know where the Schwinger bosons work much better than spin wave theory, right? For a real. So the other context in which one can show that Schwinger bosons work really well, and I will close with this, is a more trivial quantum critical point. Consider a bilinear system, a square lattice with a strong interlayer coupling. So in such a way that both interactions are antiferromagnetic. If J is dominant, you have singlets on every single bond, right? Roughly speaking. And if you increase J prime, there will be a critical point, the quantum phase transition into an antiferromagnet like this. So for this simple problem, you can first say, well, what if we use the semi-classical approach that I was describing in the first part of the talk? You can use SU4 basically to describe each dimer. It's a 4-level system. And if you do that, you use SU4 spin wave theory, you get that the critical G, the critical ratio of J prime over G is 0.25, while Monte Carlo tells you that it's actually 0. So you don't get a very good agreement with a classical theory, even if you use SU4. If you use SU2 Schwinger bosons, you get 0.235. Doesn't look good. But if you use now SU4 Schwinger bosons to describe these dimers, you get 0.42. So you get a value that is much closer to the Monte Carlo result. Moreover, you generalize the story that I just told you, and you introduce now bond operators in terms of these SU4 Schwinger bosons. Now you have 4 bond operators. The important thing here is now we have 4 bosons because our dimer contains 4 levels, the singlet and the 3 triplets. So we need 4 bosons. These are the so-called bond operators introduced by Batt and Sachs-Steph. But the nice thing about this approach, in contrast to Batt and Sachs-Steph, is that with this approach, you can describe both sides of the phase diagram, the paramagnet and the magnetically ordered state. And actually, this is the agreement. I mean, this is the comparison between the Schwinger boson approach in terms of SU4 boson. So what I'm doing now is generalizing the Larsen approach now from SU2 to SUM. The circles are quantum Monte Carlo results. The line is the Schwinger boson approach, right? So once again, you can see near a quantum critical point, now at kind of trivial quantum critical point, the Schwinger boson approach works much better than any of the semi-classical approaches.
Can you remind us how you fixed N to be 4?
Good, excellent. Because, my fundamental units here are dimers, right? So I have a singlet and a triplet,
Yes.
4-level system. So what I'm doing is I'm describing that in the same way, in the same spirit that I was right with 4 bosons. That's the way you get it before, right? Because the bilinear.
And I remember in these systems that were studied very extensively by Sebastian when she was a graduate student, and there was a dome of antiferromagnetism after the critical point. Can you reproduce that also?
Yeah, right. Yeah, I was working with him. Yes. Yeah, no, precisely. That is the point. For these kind of systems, this kind of pressure and use phase transitions, actually it's much better to use Larsen. But Larsen
Using the 4 states to represent the triplet.
Exactly.
Very nice.
Exactly. So you use Larsen, but your starting point is not SU2, it's SU.
Yes.
And
Very nice.
so Good, and basically, the story is that, you can not only compare the transverse modes, you can also compare the longitudinal mode. There is a longitudinal mode on the ordered side that will be overdamped. If you stop at the saddle point level, again, you get the spurious mode. But, if you add this counter diagram that I was describing, you get rid of the spurious mode and you get the overdamped longitudinal mode on the magnetic field, which is another thing that you will not get so well, with the semi-classical approach. So, moreover, you can also reproduce the static correlation functions of the integral over omega of intensity of these peaks. Again, circles are quantum Monte Carlo, and the full line is the Schwinger-Boson approach based on SU4 Schwinger-Bosons. So with this, let me stop so we have time to discuss. Let me just say that, classical and semi-classical approaches based on SUN coherent states can accurately describe the dynamics of many magnets, realistic magnets. You don't need to go to the exotic system. Near quantum critical points, simple quantum critical points, or the less trivial ones associated with transitions into spin liquids, it's better to use a large N expansion. Again, it's useful to generalize this large N expansion, so your starting group is not SU2, but can be SUM. And basically, an important thing when you use these large N approaches is you need to go beyond the saddle point if you want to describe ordered phases. There are counter diagrams that cancel the single spin unfolds. And then something that I didn't discuss, you can get the correct ordered moment magnum velocities with these triangular antiferromagnets. And moreover, you can reproduce the linear spin wave limit by sending S to infinity. So you can do Schwinger bosons and then send S to infinity, and you will recover the linear spin wave result, which is something that was one of the problems, with the saddle point approach. Once you add the counter diagram, you recover the large. And finally, you can describe, these other kind of quantum critical points, which are simpler, also, with this large. Thank you very much.
Talk. Let's have some questions.
Yeah, Elliot, a general question for the strategy. Imagine I don't know about experiment in Monte Carlo. So you said, so the question is, what should be my guiding principle to choose which representation and whether I should take bosons or. So you said that the N should be chosen corresponding to the number of states that I have in the cell. That's sort of one guiding principle. And now, for example, for the Schwinger bosons, so when should I do so you have the example that the SU4 Schwinger boson works, but the other one doesn't.
Well, right, so what is intuition? Behind, do I understand? Well, what for instance, here is that, the way this transition is happening is because you have, in the semi-classical approach, you would think, in order to describe a continuous transition from here to here, you need to have some linear combination of singlets and triplets. So again, you need to be able to describe a coherent, you need a coherent state in SU4, which is the motional linear combination, right, in order to classically describe this transition, right? So if you are going to do large N, for the same reason, you want to keep the singlets and the triplets, right? If you want in your path integral, when you are doing large N, essentially when you go from SU2 to SU4, what you are changing actually is the coherent states or that you are using to expand the identity in path integral, right? So I know this is, okay, when I write the path integral formulation, this one here, you can write the path integral formulation expanding the identity in coherent states of SU2 or coherent states of SUN. Right, in a transition, again, where you are going from something that has, triplet character or, character is a product of two local moments to something where, you get entanglement, because spins are start forming a singlet, you want to have all these possible states in your variational space in some sense, right? So you want to use coherent states of SU4, right? To basically account for the transfer of weight, for the triplet to the singlet, right? So, or in other words, you want to have that intra-dimer entanglement built in your approximation, right? So the singlet has to be one of the coherent states of your theory. You don't want to have to build that entanglement through, interactions, right? I don't know if maybe.
So are you able to give us a handbook that tells us, here's the model, this is the prescription for
Yeah, right.
for both, and that'd be
Yeah.
really useful, right?
Okay, so
The
I mean,
rule
like,
is, the
let
rule
me-
is the
let me-
multiple number equals to n, for your SUN. I think.
Right, so let me go back to your question. So address it. So I mean, like, why should I mean, of course, you can imagine many other classes. Right, you could use that joint representation, SU3. So imagine that you have now a problem of dimers, right? But now you have two spin ones here, okay? And the interaction is some SU3 isomer that splits the ideal states into a singlet and an 8-dimensional representation, right? So now, okay. And let's say that splitting is big. Okay, the low energy theory, you would like to keep that rep of 8-dimensional. So probably in that case, it is convenient to use that joint representation of SU3, the 8-dimensional representation to describe that problem. Right, and in that case, again, you're going to get a classical theory where the phase space is not CPN -1, it's a flat manifold. The second homotopy group is Z cross Z, so you would have monopoles with two flavors and things like that. In that case, you're thinking in terms of a low energy theory. So what my low energy subspace is an 8-dimensional rep of SU3. So, it's natural to use that classical. Right, and the way you have to think is the same way you think in physics, when you are identifying the target space of the other parameter. So, well, it's essentially identifying the right degrees of freedom. For that, you need some intuition. I cannot give a recipe, right? But it's supposed to be
You're pretty close to having.
right. So I mean, it's more like about what is the variational space,
Yeah.
right, of low or relevant physical states.
And so here this dimerization is between two layers, right? So,
Yeah.
but could you generalize it and take the transition between, let's say, an antiferromagnet and the VBS state? And how would you deal with I mean, you have singlet and triplets and you can construct coherent states, including both.
Exactly.
But still, the VBS state spontaneously breaks a discrete lattice symmetry. So how can you avoid breaking the symmetry by hand in your construction?
You mean?
So I mean, let's say in 1D, you still have Z2 symmetry, right, for the two VBS orderings. So here it's easy.
Yeah, here is given, right?
yeah.
So if it is not given, then it will be arbitrary, to break the translational symmetry and introduce units. Yeah, right. So what you can do is, if the symmetry is broken, then start from some approach like this one and then do the small oscillations or something like that. But
so there is no Schwinger boson treatment along these lines for the confined quantum criticality.
not along these lines. Not along these lines.
Other questions? We have 10 more minutes, that's Tony.
So going back to the earlier part of the talk about the levels, a lot of times, or in some complex oxides, rare earth oxides, you have large J electrons with crystal split.
Exactly.
And so generally the belief is that if your temperature match, so say you have a ground state doublet and some splitting delta above it, the temperature sufficiently small than delta of D in your diagram, well, the other one at least, I mean, you would have the SU2 type of.
If you have a ground state doublet,
Exactly.
and the gap is big, exactly the temperature.
Whereas in your discussion, it seems that actually the symmetry is important, which one should consider how many doublets there are present, what's the large J, what's the actual J of the system. So how do we reconcile the two pictures in a sense? So is there a low energy, low temperature picture where your SU3 or SUN would become SU2 again?
Yes, I mean, like if you have, that is indeed a clear example of where you want to use SUN, if you want to include more than one multiple in your field. And you may have different reasons why. I mean, maybe the change in interaction is comparable to the gap. Right, so you need to include more than one multiple, then you will naturally use SUN with the different multiples. And going back to your question, yes, so if you do that, and in the low energy sector, you have, subset, it will be great, right? So SUN will contain that.
But so in the other slide that you had, the one where the doublet was down, just the negative.
Yeah, the negative, yes. The doublet is the ground state and then the.
Exactly, where the
singlet.
nice ones.
Yeah, this is not.
That one, yes. So you're saying that the physics of this system would exhibit SU2 rather than SU3 behavior if you go to low enough temperature or energies with respect to D.
No, that is not here because this doublet basically is, 1 and -1. So actually, the low energy excitations within this doublet will give to a problem. You need to
They necessarily have to, okay. But in that case, if the excited state was a doublet instead, so if you're, then in that case, would they be SU4 or they would be SU2 when you're at low energy? Sorry, this is a big thing.
So it will be SU4, right? So, but at low energy, you will see only one mode.
Yeah.
Okay, and that mode will be the same mode that you get if you only consider that. Actually, there is something nice, the way, I mean, remember, I discussed the SU2 classical length. And the way you take the SU2 classical limit. Actually, there is a better way of taking the SU2 classical limit is use coherent states of SUN and then constrain to CP1. The classical theory that we are going to get contains renormalizations that are not present if you simply replace the operators with exposition.
Okay, more questions. Questions from the 5 people with their laptops up. I've asked questions. Questions, more questions. Yeah, Jamie.
Thank you for being. Oh, I see a little bit about how dimensionality enters here, because, for example, some of these techniques work better in lower dimension.
No, of course, if you are using semi-classical techniques, the higher the dimensionality, the better, right? Because that gives you, I mean, in general, all of these control parameters are not really small, right? So actually, you rely on something else. That typically is dimensionality and large combination numbers. Will render your semi-classical treatments more accurate. Right. So yeah, that's an excellent question. But even in 1D and then show results, allow a certain temperature, there is a point where the classical crossover and the classical theory works. Actually, for beta X model, right, there is a temperature above which this classical approach works, actually reproduces very well the exact quantum mechanics. So unless the model is integrable, typically there is a quantum to classical crossover. The big question is, what is the classical theory that you need to use above that crossover temperature to get a good approximation?
So Dora, yeah, Cristian, thank you very much. Nice talk. So the barium cobalt thing, antibody that yes, you showed very nice spin on and also on composition behavior, and you mentioned that you may say that the system is proximate to a quantum recap point.
Yes.
Maybe that is quantum recap point separating in liquid.
Yeah.
And 120 degree of that.
Yes, indeed. We have a sequence. We are right now working with, this is kind of a rational approach to quantum spin liquids. Let me explain what I mean by that. There is a sequence of the opposite compounds where you can tune this ratio, J2/J1. And as you get closer to this point, you see that, this continuum becomes bigger, the ordering temperature becomes lower. And we are working right now on one material, the sodium version, that actually sits here. The ordering temperature is, there is no ordering temperature. And, the experimentalists have some exciting results that we are going to publish soon. Supposedly that material is here. The only problem, the only caveat is sodium. So, for this order, sodium is not.
Yeah, so I have further question.
But there is a material
So you are saying that you can allocate this day two over day one
Yes.
by actually identifying the spectrum.
Yeah, exactly. That's what we do is we go, I mean, we apply magnetic field, go to the plateau phase where the system becomes semi-classical again.
Yeah, but
Field.
of course, this is within approximate, I mean, the approximation of the model and change of the what governs the physics,
But with magnetic field, you make the system classic. I mean, you make the approximation
yes,
classic.
it's sure, but always there is some concern about disorder.
Absolutely.
Yes, so how do you tackle this? Do you have any perspective?
I mean, that's a question for the experiment. I mean, how do I tackle?
Do you have any idea how to introduce that, or you don't?
You mean introduce disorder in the
Ground
approach,
state is always a question with our.
whether it's or not is disorder? I mean, I agree. I mean, disorder is one of that, but you know, the whole point of doing all this exercise
Yes.
is to show that, you know, with a clean theory,
Yes.
I mean, you can reproduce the dynamics. That's a way of studying. I mean, if you think of the way lattice liquids or, you know, spinos were reported in 1D, okay, the most convincing evidence was to show the agreement with Bethe ansatz. But in systems that actually order a certain temperature, but, you know, above a certain temperature, above the ordering temperature, you see a continuum that you can reproduce very well with the spin condition. So actually, that is part of the motivation for developing these Larsen approaches.
So you can apply, if you substitute sodium by potassium, you can actually develop
Yes.
ordering.
I mean, the ordering temperature goes to zero and there is, you know, if there is a gap in the spectrum, you can use Lipschitz Matisse theorem of degeneralization. To argue that, you know, the ground state must be degenerate if there is a gap in the spectrum. And the ordering temperature is zero, that degeneracy should be topological. Right, so the only spoiler would be disorder.
Yes, hi.
So if we go to the Heisenberg limits, does this quantum modes become also zero and can graph this one?
No, that's an excellent question. So no, it's not zero. They have finite energy. The question is, how do you get rid of them? Because they are not true quasi-particles. And the way you get rid of them is by doing a one loop correction. So, correct. So imagine that you started with SU3, right? You have quadrupolar and dipolar modes. Let me show you. This is going slowly. But I have one slide for this. Okay. This is a slide. So that's what you are asking, right? So it's essentially you have a Heisenberg model, you have the quadrupolar mode here, but you see it's inside the two-minor continuum. So once you do a one loop correction in SU3, this mode becomes overdone. That's the way you get rid of it.
Oh, sorry, but this is for quantum T or?
No. This is for the much more than J. We'll put it to zero. We'll put it to zero. So that's the way you get rid of it. You need a one loop correction. So in general, if T is large, you're going to use SU3. If T is small, it's better to use SU2 because you get rid of the mode.
That's interesting. One of the situation where SU2 works better. So
Yeah, exactly. But even in that, you know, what I was saying, right? So, I mean, even imagine that you want to extract this value of T. Actually, you will extract the wrong number if you use the plane. The best thing is use SU3 and then constrain to CP1, and you will get a renormalization of V, and you know, then you will extract it. So many 1/S corrections appear as a renormalization of the classical theory. If you simply take the classical limit in SUN and then you constrain to CP1. So you get a lot of 1/S corrections without doing any perturbation. It's all analytic.
Beautiful work. I'm afraid we're going to keep on time. We have to stop this discussion, but can I encourage you to continue the discussion with Cristian afterwards? And we'll meet back in 20 minutes.